Well, now we're going to define what it means for a sequence to be bounded. More specifically, bounded above, or bounded below, or bounded. And then we're going to state and prove a theorem that's related to the boundedness of a sequence. A sequence AN is bounded from above if there's a number above it that is greater or equal to every single element in the sequence. So mathematically, using our symbols, it would be this. It's bounded from above if there's some real number m such that every element of the sequence is less than or equal to that number for all natural numbers. Similarly, on the other end, bounded from below, AN is bounded from below if there's some number, capital S, such that every single element in the sequence is greater than or equal to that capital S. And finally, the sequence AN is bounded if it is bounded above and below. So you have an upper bound and a lower bound. All of the sequence elements fall between those two values. We'll take a look at theorem 1.2, what it says about convergent sequences. If AN converges to the real number A, then AN is bounded. Another way of saying that would be, and in a more general way, would be all convergent sequences are bounded. All right, well, I know AN converges to A, and then I need to prove that it's bounded, which, by the way, means I'm going to have to find the capital M and the capital S that work. All right, let's just start off with giving epsilon a value. It can literally be any positive number that you want it to be. I just chose one. You could choose a half, you could choose a million, it doesn't matter. Let epsilon equal 1. Then, let n be a natural number. Let it be such that n greater than n, meaning little n greater than capital N, implies AN minus A is less than 1. I could have used the letter epsilon there instead. I actually didn't even have to use epsilon as a variable in this proof, but just to make it look more like the definition, I did that. So let n be such that if n is greater than capital N, that means that the distance between AN and its limit is less than 1. Why am I allowed to do that? Because it's true for every positive number epsilon. I could have chosen epsilon equals 0.00001 if I wanted to. Now notice where we are already. An infinite number of the elements in the sequence, in fact, all of them starting with an index, with every index greater than capital N, is bounded above by A plus 1, bounded below by A minus 1. Let me put that in parentheses here. That means AN is in between A plus 1 and A minus 1. So for most of the terms of the sequence, that's a lower bound. Oops, I did that backwards, didn't I? This is an upper bound and this is a lower bound. All we need to deal with now are the first few elements at the beginning, going up from A1 up to A capital N. So I'm going to just say let S equal and let M equal. Let's see, I'm going to use S as the lower bound. It's going to be the smallest of A1, A2, up to A capital N, and then the number A minus 1. And I'm going to let M, capital M, be the maximum of A1, A2, up to A N, and A plus 1. Therefore, AN is in between S and capital M for all natural numbers n. And that's the definition of AN being bounded, and that's the end of the proof.